Sorry for the delay for the first day, so it takes time to set up. And I think the first question would be, do you have access to Canvas shell of this course? No. Okay, I still didn't receive the email for that. So sorry for that. And if you had known me from Heat Transfer, you know I never get luck with Canvas. So we will try to fix it up for week 1. So I think starting from week 2, you can find all the documents you need with that. And as I mentioned in the email I sent you, so for week 1, the tutorials will be used to introduce as a review on advanced thermal fluids, which is also known as heat transfer. And so in the tutorial, we will try to finish the review and also some tutorial problems on that. And on the lecture Thursday, we will do the introductions on the refrigeration cycles. So it sounds like you will have a 3-hour lecture for week 1, but don't feel stressed about that because the review would be really easy if you have learned the heat transfer concepts. So an introduction to our teaching team, and I'm very glad to see some familiar faces because you have already taken heat transfer. But like for this course, Applied Heat and Mass Transfer course coordinator Kiao, you have his contact and the room number. I will also show you later on Canvas how to find the consultation time. So within the consultation time, you can just drop in our office, and if you get any questions, we'll answer that for you. So I am the tutor, so I will take over all the tutorial sessions. And also, according to previous years' students' comments, that they do really need some more people to help with the tutorial. So we asked another 2 PhD candidates. One is Kendra, and another is James. I didn't see them here. So these 2 will help you with the 3 computer labs. And so I think they will come and help the tutorials, but they are also like just starters. So we will try to manage it in a way that we give you the help as much as we could, but also please like understand they are just the starters for these lab instructors. And okay, so for week 1, as you are coming here, I will introduce to you firstly the structure of this course, because if you could know, if you had like look at these weekly activities, you will know you need to learn like boiling, condensation, heat exchanger, fins, and also later psychrometry. So you might be wondering, like every week we are shifting a topic. Are they closely related or are they applied in different areas? So later I will introduce the structure of this course, why we need to learn all those things, and you will see actually they are closely connected. And also the schedules of this semester, like how the labs are arranged, I also need to explain that to you. And also when do we take the midterm test and what's the due dates for all the assignments. And for the assignments would be the thing you might want to know first. So we will have 3 experimental labs on thermosiphing, heat exchangers, and evaporative cooling. For thermosiphing, so these are on week 3, week 6, and week 9. For thermosiphing, we don't need you to write any lab report, but this thermosiphing will be introduced in the lectures and will be tested in the midterm test. So if you want to get good scores on the midterm test, it's better that you come to the lab and know what's the structures of the thermosiphing, how to do the calculation of thermosiphing. So thermosiphing is about the concepts of boiling and condensation. And when we move on to week 6, we need to do heat exchanger experiments, and you need to write a lab report on that. And later on week 9, you do the evaporative cooling experiment and also a lab report. We have changed the due dates for those 2 lab reports into 1, so that due date is on week 11. That means you have enough time to finish your lab reports, but it's better that you organize your time well. So those 3 are experimental labs because this course is closely related to real-life applications. And we only have 1 assignment. I don't remember which week is due, but later we will see that. So the shell and tube heat exchanger design is basically that you need to come to the tutorial sessions and learn how to solve problems regarding condensation and heat exchangers. And this design is kind of a combination of the several weeks, and you finish this design basically by complete the calculations for different steps like condensation, heat exchangers, and then that's basically it. It's more or less like a practice. Then you will have the mid-test in week 5 and exam on the last in the exam period. And also we will give our responses to in terms of with regard to the CES comments, because you have spent your time giving us feedbacks, so we also let you know what's our response on that. So first of all, let's do the easy things on CES feedback. That students say the good thing is we are closely related to real-life applications. So that's the best thing we have, so we will keep on that. But also, these two are not really related. So the bad thing would be students say we have the tutorials actually prior to the lectures, which is not really good. But unfortunately, that's something we cannot change. We try to call the school, but they don't change that. So, so in terms of this part, we try to change the schedules every semester. So if we have tutorial prior to the lecture, that means the tutorial next week, I have to spend a little bit time to review the contents on the lecture before, so the week before. So that means I have to consider between these two comments. One is students would say, I should spend enough time to show you how to solve these problems step by step, instead of just telling you do the practice. But we also notice that some students say, it's better you have time to attempt solving this problem, and I should better not to go through the solutions first. So I was really struggling between these two things, really. So because I believe that if I ask you now, you will still have different opinions. So on this one, I would say because this semester we have the tutorial before the lecture, so I have to spend some time to review all the contents, then I will have less time to give you to attempt all those tutorial problems. So that means we take the first one, that I show you all those tutorial steps, how to solve the problem steps first. So if you really want time to attempt trying to solve the problems, please take the time before the tutorial. So you can do that on weekends and try to see if you get any problems, and then come to the tutorials and do all those things. So that's the best solution I can find. And also, the third comments would be, you would say you want longer tutorials and more examples because you think the midterm tests and exams are much harder than the tutorial practices. I would say I will try to solve these problems because I will keep tracking the tutorial problems. If I see like midterm test or exams go a little bit beyond the tutorial scope, I will let you know. For example, we like a revision, or I provide you some more practices to do that. But basically, I would say don't worry about that because the tutorial problems are already difficult enough in this course. So that's something to let you know. And the last one to explain is students they would prefer that we record the tutorials and lectures. But the problem is when students come to the tutorial sessions, they find we have less interactions because I have to stand here in front of the computer. So I think the best way is I will try to do more interactions with you. And so to the students who is watching this video at home, you need to know that, of course, I take the students come to the session as the priority. So if you feel this recording cannot satisfy you, please come to the tutorial sessions. So that's the thing we need to explain to you for the CES feedback. And then, okay, So on week 1, as you already know, I've explained what we need to do on week 1. And some changes would be, we have 1 hour tutorial, you have another lecture for 2 hours, and you will find there is actually another 1 hour practical lab allocated to you. But this time is almost free, except week 3, week 6, and week 9. So that means in this time slot, I will make this as my consultation time. So I will stay at my office. If you have any questions, you can drop in my office and see if I can help you. But for this time, it's actually allocated to you, but we didn't arrange anything because we already received lots of comments. This course is too stressful as a 4th year elective course. So we did cut down something for you. But for this time period, I hope you could still utilize that to continue your practice. Because in the tutorial, I might only spend time do some major steps. So in the practical lab after the lecture, you can spend your time repeat all these calculations according to the solutions. So that is some preliminary thoughts. Okay, so a very important reminder is everyone, if you receive the lecture link, or currently you don't have access to Canvas, so if you go to your lecture slides here, as I showed here, and if you click onto the link, you will see there is a sign up sheet. Anyway, I cannot open it up here. So when you open up this sign up sheet, you will see you have some instructions here. I told you about how you should sign up for different groups. Group A and Group B. So I think that's clear enough and you could do that. If you have any questions, just email me. And class test. So for this one, it's better you finish it before the end of week 2 because the first experiment is on week 3. And class test will be on week 5. And we need to separate students into 2 buildings because this room will be too crowded for class test. And I think later, Kiao will organize these things, maybe according to student numbers. So half of you will be staying in building 251, and another half will be staying here in this classroom. But we will keep you informed later, but you need to know we'll be on 2 places. And then just case study due on week 7, and lab reports portfolio. So that's 2 lab reports due on week 11. So that's some important reminders. I guess you don't have any questions now. No. Okay. So the timetables, lectures 2 hours, tutorials 1 hour. So for the lecture, although it starts at 3, we will usually take 10 minutes to wait for other students to come. So it comes like 10 past 3 would be the formal lecture. And for the tutorial, because we only have 1 hour, so I hope we could start sharply. But I realized today we have a tutorial before that, so maybe we will try to start on time. And also for the practical lab time allocated 5 to 6 on Thursday, hope you could still use that for self-studying. And experiment labs, just here a summary for what I've explained before. So for this course, our expectation is you have already studied thermodynamics, fluid mechanics, and heat transfer. So now I just want to know, is anyone here hasn't studied the heat transfer last semester? Can you show me your hand? Okay. So yeah, maybe if you have any questions, we can just talk individually about that. So if you have learned all those 3 courses, then the future lectures or tutorial is basically teaching you how all those concepts are connected to real-life applications. And so our expected outcomes would be you will get enhanced employment and work-ready skill sets. Because basically this course is based on introducing some building services regarding HVAC system. So hope everyone knows HVAC stands for heating, ventilation, and air conditioning. We use this one as our example because HVAC system is an ideal example that you have condensation, boiling, and heat exchanging, and also cyclometry on that. So by using this example, where you can integrate the concepts within heat and mass transfer onto this HVAC system, you can actually apply it to a wide range of applications. Okay, so the materials we will provide to you is lecture slides. We will try to upload them maybe like, I'm not sure, because the lecture is on Thursday, so maybe Tuesday or Wednesday we will get the lecture slides ready. And you already have the what is that? Tutorial notebook for the whole semester. So if you take time to have a look at it, then you will know what kind of problem we are going to solve for the whole semester. The experiment lab notebooks, we have 3 labs for you to do. So you will receive the lab guide per session, like maybe a week before that. And tutorial solutions will be provided to you. I hope it's just before the tutorial, because I don't want you to check the solutions quite early. I don't know if that's correct or not, but it's better you try to solve the problem first and then look at the solutions. Or else you come to the tutorial, we'll do that together. And tutorial and lectures will be recorded, so if you cannot make it on the tutorials especially, you can check the echo system recording. And the prescribed textbook would be listed here, and we will also provide some chapters to you for additional readings. So all those things are on Canvas under each weekly modules. Okay, so the way of each assessment listed here. If you want to have a read about that, you could refer to your lecture slides. Okay, so we could start to introduce the structure of this course, but first of all, just to show you some pictures. You are familiar with this split air conditioning system, so it cools down the indoor environment, or in the winter it heats the air up. So we are basically introduce this system, but I hope you know that this system is just a very small fraction of the applications for residential buildings. But if you go to some industry areas, for example, for hospitals, hotels, and all the other kind of commercial buildings, they actually need a very large capacity for cooling or heating. So for houses, it might be 1 to 10 kilowatts, but for the other buildings, they might need several sets of chillers, which is a very huge cooling capacity. So in this system, if we only look at this indoor environment, for example, let's take summer as an example. So you will have the air exchanging the heat with some pipes inside this coil. So in that way, it's actually a heat exchanger. So your heat within this room is taken away by the cold water pipes inside this one. So the cold water pipes is connected to this chiller, and this chiller contains this refrigerants. So the refrigerants is taking away the heat that's being absorbed from the indoor environment. So it's another part of heat exchanger. And within this one, because it utilizes refrigerants, and later we will learn that it involves boiling and condensation. So it's very important that we know how to calculate the amount of heat that's being taken away by both from the indoor environment and also the heat exchange in these chillers. And because inside this one, if the chiller cool down the cool water that you use to cool the indoor environment, it also needs some other part to take the heat away, for example, to reject to the environment. So in this part, it needs another connection to the outdoor environment. So we could use, very commonly, we use cooling towers. So you have these cooling towers exchange heat with this air. So hot water will be cooled down by the air, then the hot water being cooled down and go into the chiller. that forms a cycle to cool down the refrigerants. So there are several parts you need to learn, and we will introduce this to you week by week. So that's basically what the machine looks like. So if we go to the schematic photo of that, this is the indoor environment. So in summer, you cool down the air. In winter, you heat up the air. If we take the summer to cool down the air as the first example, then we will need to provide cool water to exchange heat, to take away the heat from the indoor environment. So cool water will be heated up by this air and goes back to be cooled down again and goes into this circulation. So in this part, later, maybe from week 8 or 9, we will learn what's the heat exchange inside this indoor air part. But for the first week 1 and week 2, we're actually looking at refrigerations. So because we want to cool down the water that's going through these cooling coils, so we are wondering how can we cool down this cold water. So it's basically by having these refrigerants, and to, as we learned in the thermodynamics, we have this cycle. You go into compressor and go to condenser. So in the evaporating part, it cools down. The cool refrigerants absorbs heat. So you will see this red color means it's being heated up. And we want to utilize the cold water from the cooling tower to cool down the refrigerants, so it comes to continue to this cycle again. So for week 1 and week 2, we are on refrigeration cycles. That means we need to know pressure and enthalpy charts, and also what's the COP concepts. And when we finished the refrigeration cycle, we are actually looking at boiling and condensation, because the mechanisms is we want to know how much heat could be absorbed or being rejected caused by this evaporating process. So in the boiling and condensation part, it's some calculations. Just utilize experimental correlationships. For week 4 and 6, this is related to condenser design. So maybe in this part, you need to start your assignment, which is just finish the condenser design. And why we need to look into this condenser is because it's closely related to heat transfer. So you know, if you are going to find a job, you need to make yourself like competent. And in that way, although we know all the mechanisms in this system, we still want to know what we can contribute to the current system. Can we utilize something to improve the efficiency of the heat exchanger so we could have a more significant heat exchange within this one? So that we need to look into the condenser design, which would be between like tube-in-tube and plate heat exchangers, how this works, counterflow, parallel flow, such things like that. So that's for week 4 and 6. And if you continue to look into the details, you will know that adding fins on those tubes will also contribute to the improvement of heat exchange. Because as we said, flow regime matters. Whether it's laminar or turbulent, it will have a different heat exchange results. So in week 7 and 8, we will learn like for conductions. By adding things, how could it help the heat exchange? And the last 2 weeks, when we finish learning all the basic concepts within this refrigeration cycle, we will look into the combined heat and mass transfer. So that's basically this indoor environment. And we will look at how temperature and the humidity changes would matters to the final results of this system design. So as we mentioned before, this HVAC system is not the only application that utilizes heat mass transfer. It's just the best example we can find. So by introducing all those concepts to you, this is summary. So boiling, condensation, heat exchanger, and also some conduction problems relating to fins and convections. And in the last, the psychrometry would be related to not only heat transfer, but also mass transfer in terms of the humidity change. So you will learn all the concepts, and also it's closely related to all the applications in the real life. So you will get this connection, and maybe that would help you to find a job easily within this area. Okay, so that's basically what I need to introduce for the topics of this part. Then if we continue, that's the review. So the review is not difficult, or I don't even need to spend time to introduce this. But for example, this is from fluid dynamics. And fluid dynamics, sorry, check the time. Okay. I'm putting these slides for the head loss for friction loss and later the minor losses. Is because this fourth year course is we try to solve more comprehensive problems. So you will need these two slides in the condenser design, the assessment. Because when we provide you a design that we want to design a good condenser or heat exchanger, so condenser is basically a heat exchanger. So you need to consider not only the heat transfer effectiveness, because if you want to create a new product, you need to consider so many aspects, and so the pressure losses within that product is also a very important aspect. In this course, we only teach you how to find out the heat transfer rate Q dot, and we presume that you know how to find out the friction losses. So later, when the assignment is released to you, you will see you need to find out not only the heat transfer part, but also to compare, because you will have different structures for the heat exchangers. For example, this is for heat exchanger, you have this very sharp inlet and outlet, while this one have these bands. So if you go back to check some tables, you will find different structures will give you these like different minor losses, and also different length of the pipes would have different in these pressure losses. So that kind of parts you need to consider in your assessment for this condenser design. So that's the part for fluid dynamics. And then also we need to review, as the thermodynamics, we have the energy balance, but it's very easy. If we have a system, and if we are having this heat transfer to be transferred into this system, then we will see all the heat transfer that's being absorbed by this system, and if we have this shaft input, these two parts will contribute to the energy change of this fluid that's flowing throughout this system. So the energy change, which contains these parts as the enthalpy change, the momentum change, and also potential change. But usually in some common systems, especially for in these courses, you might not observe very large change in the kinematic change and also potential change. So we would assume these two parts would be negligible. And when we consider if there is no shaft work input, this equation would be simplified as all the heat transfer goes into this system would be equal to the energy change of this fluid. And in this course, we utilize the enthalpy, the concept of enthalpy a lot, because from the enthalpy you could find out what's the temperature change, and that matters to your calculation of like heat exchangers in the future. So that's the basic energy balance we need to know as a review. And another very important part in this one is we will start with boiling and condensation. So you know boiling and condensation is a matter of phase change, And if you still remember that we have this enthalpy change, like the latent heat, later you will see a table. So in the lectures, we'll explain the details to you. In this course, we will also need to calculate what if there is only phase change, but there is no temperature change. Because if you consider from the ice with 0 Celsius degree and it needs to be melted into water, but still 0 Celsius degree, you are still absorbing a part of energy, but how large amount of the energy is that? And we need to provide to the systems. So the phase change calculation is also important in this course. And the pressure enthalpy diagram. I'm not sure how familiar you are with this, but this diagram is really important because we need this to solve the tutorial problems. And I think you also need this in your assessment, so the condenser design. And also, you might need to know this for the midterm test or the exam. I can't remember which one is that, but it will be assessed in either mid-test or the final exam. But because this is for the previous several weeks, maybe, in the test, so you need to get yourself very clear about which line represents these physics. For example, currently we have pH diagram, which is pressure and enthalpy. So this curve separates the subcooled liquid and the saturated liquid on this curve, and on the other side is superheated. And if you draw a horizontal line, that's constant pressure, but the constant temperature would be like a vertical line first, horizontal, and go to the superheated part. So it's a little bit complicated, and it takes time for you to understand this. So when you are paying attention to the lectures, please pay attention to this part especially. You have learned that, but this get forgotten quite easily. So that's some preview. Okay, so for this part, I could see you are already very tired. And we could do a very simple problem, so to give you confidence. For this case, we can, let's just do this together, or you can write down your notebook what's the formula for this one, how to write down. So this is a really simple one because you only need Q equals to same delta T. Something, maybe I need to explain that this is quite simple because we always use delta T. So it doesn't matter whether it's in Kelvin or in Celsius because you will find out they are exactly the same. But it's just in the test or the exam, students get confused because they see the units for specific heat. Sometimes it's listed as kilojoules per kilograms per Kelvin. Sometimes it's per Celsius degree. But if you have done enough practice, you will see it doesn't matter, and also it doesn't mean it's a wrong value that you have to convert Kelvin or Celsius. Because this is basically saying to have a material, a kilograms of material, to increase the temperature by 1 Kelvin or 1 Celsius, how much energy, kilojoules, it needs. So in this one, the only thing you might neglect is if we give you specific heat as kilojoules, then your Q dot heat transfer rate will be in kilowatts. And if we give you like joules per kilograms per Kelvin or Celsius, it will be like in watts. So the units matters. So in this case, it's the very simple equation. Another one practice is actually the same. It's just we change a material. So the air has a specific heat as this value, and we have the water as another specific heat. So with this one, if we tell you what's the Q dot value and you need to find out what's the temperature change, you could also do that as long as you get everything correct. So you see this one we need mass flow rate, but you are only given a volume flow rate. So you know how to convert volume flow rate to mass flow rate by multiplying the density. So very simple problems. And some other things is actually for this tutorial to review on heat transfer is conduction, convection, and radiation. So the equations listed to you is already for conduction, but basically we would say what we need to review is Q dot is just delta T on R. So what is R? R is the thermal resistance. So for conduction, R is L on Ka. Convection is 1 on Ha. And radiation is a little bit more complicated. We don't consider it here. So if we just consider like conduction and also for cylindrical shape, it's a different expression. So you just look at the slides, and I'm not writing down on the board. So I hope you still remember all these concepts. Then the only new things we need to introduce would be, in this course, we want to express the heat transfer in a format as UA delta T. So if you remember for convection, it's Q equals to HA delta T. The H is the heat transfer coefficient, and we say convection only happens between a fluid and a surface. But here, we would say this could contain conduction as well, because this we say is like overall heat transfer coefficient. So although this is a new term introduced to you, but you will find it's actually really simple, because if we just utilize these two concepts, then you will find out that the U value is just 1 on RA, or R is expressed as 1 on UA. In the heat transfer course, you already learned how to calculate the total resistance. If it's serial network, you just add all the resistance together, and if it's parallel, that's the reciprocal of that. So in this case, if we ask you to find out the overall heat transfer coefficient, it's basically you need to find out the individual thermal resistance for convection and conduction. Add them together, you will find the total resistance. In that way, you could find the overall heat transfer coefficient. And another new thing to introduce, which may be too early for week 1, but in the tutorial problems, you might need this. And this is also really simple, because we want the resistance to be used in the serial or parallel network. But if you have the fouling on that pipe, and there will be fouling factors given to you in this table. So you will have these fouling factors. Although the fouling factors are expressed as R subscript F, but you cannot use this as resistance directly, because the unit is square meter per Kelvin per watts. So you know the resistance units is Kelvin per watts if you use delta T divided Q dot. So that means if you want to find the resistance on the fouling parts, you just use this divided by its area. Then you can use this part into the calculation of the total resistances. So that's the thing I need to introduce for the practice. In this case, I also want to try to see how you feel about that. For example, we have the tutorial problems as giving you the details. What's the distance, like delta x is 0.21, 0.1, and 0.05. And also the conductivity, K1, K2, K3 is 0.7, 0.44, and so many parameters given. But I was wondering if I could simplify this problem in a way that we are giving you T1, H1, heat transfer coefficient here, delta x 1, 2, 3, and so you can write down the equations, the formulas to solve this problem without doing the calculations, because I guess that saves some time. So maybe we could try this first. This is the tutorial problem for week 1, and if we just ignore all the parameters here, and I'm giving you all those formulas you need. Let's write down what's the formulas for, firstly, the total thermal resistance and the following 4 questions. So the steps to solve this kind of problem would always be, because you are given the conductivities and also the dimensions of this geometry, the only thing I need to remind you is the convection part is really could very easily neglected, but it matters in the total resistances. So every time you are considering solving a problem, when you see this block, just double check whether you have this convection part, because temperature T1 is the fluid temperature. It is not the, as I said, the temperature on the internal wall Tin. So there must be some heat exchange between T1 and Tin. So for these 5 parts, you have part 1 and part 5 as convection. So for convection, resistance is 1 on HA. So one is 1H1A, another one on H2A. And then the conduction resistance is L on Ka. So when you listed all those 5, and because they are in serial network, you could find out the value for the R total. If you find out the total values, then that means by utilizing this newly proposed concept or this term, overall heat transfer coefficient, you can calculate what's the overall heat transfer coefficient. So you will notice that although we try to utilize this form very similar to convection, but actually this part also contains like both convection and conduction. These two can be very easily converted, but in this course we prefer this overall heat transfer coefficient is because, for example, if we use resistance, when the resistance is high, we would say it's a good insulation. But in this course, we try to have more significant heat transfer. So if the resistance is really low, that makes the overall heat transfer coefficient really high. So if we just can read very directly, we have a very high value of overall heat transfer coefficient that will tell us it's a very good design in terms of heat exchange. So that's practice on getting this value, overall heat transfer coefficient. You also need to calculate this in your condenser design. And the last 2 parts, rate of heat flow, you just need to make sure what's the known parameter. You only know the temperature between the inlet air and outlet air. So that means the temperature difference of that 2 should be divided by total resistance. But the last one asks you about what's the temperature on the first part. Actually on this part. So this part contains the resistance caused by convection only, because between T1 and Tin, there is only convection resistance, no conduction. That's the surface temperature. So in that case, also because it's serial network, so the Q dot you get is the heat transfer rate Q dot throughout this system, but it also equals to the individual Q dots. So it equals to Q1, but Q1 is calculated from the temperature, T1 and Tin. This is unknown. We want to find out that. And the resistance here is not the total resistance anymore, because we only consider between the air and the inner surface. So because we can find out this using conductivity and the dimensions. So we can utilize this equation to find out what is the temperature on the inner wall. But this is based on the assumption that I assume T1 is larger than T2. But I guess you all know that you just utilize the higher temperature to minus the lower temperature, makes things easier. Okay, so that's the first practice. I also provided like the thermal resistance network on the lecture slides for you. And so for week 1, the tutorial is only on review. I reviewed this problem to you, so that's the first program. So on the tutorial handout, you have a second one. It's more complicated, but the basics are the same. So I will keep that to your own practice. Solutions is all already provided to you, right? So you can check all the solutions. If you have time, you can do the calculations and see if you are doing all this correctly. But basically, I just need you to get all the concepts correct throughout the steps. And last two slides is basically explaining that I have introduced here. We already have an R. Why do we need to use the overall heat transfer coefficient U? So it's just because we use it for different scenarios. So you can have a little bit reading on this one. And that basically is the part for thermal review. So Thursday, I will see you again for the refrigeration cycles.